Morning, students. Today we start the chapter of biasing schemes and bias stability. Last lesson we have learned what is biasing. Just we have learned what is biasing. What is the meaning of the word biasing? Now, this biasing can be done with the help of various techniques, with the help of many techniques. So we shall see those techniques one by one. From our last lesson, biasing means to provide a potential of desired polarity and value at the base of the BJT, bipolar junction transistor. And at the base means we are talking about common emitter configuration, the most common configuration. Later on, we shall develop our concept on common emitter configuration. Later on, we shall also overview the common base and common collector configuration. Anyway, in common emitter configuration, input to the transistor is at the base, and we have seen in our last lesson, you have to give a potential of desired polarity and value to the base before calling it an amplifier. Desired polarity, the base emitter junction must be forward biased. That's all. If it's a NPN transistor, then base is P and emitter is N. So base should be positive with respect to the emitter. If it is a PNP transistor, it is opposite. In that case, base should be negative with respect to the emitter. This is the polarity. Next is desired value. There is the triple question mark. How do we know what is the desired value? If you have a voltage source, you can always connect negative side or positive side to the base. But what is the value? Now, normally in your textbooks, there is I don't find a clear-cut, straight approach to tell you how do you decide on the value. Here in this today's lesson, I'll try my best to tell you how you decide the value. Now, this is a simple common emitter configuration. Very simple common emitter configuration is this. This is a NPN transistor. Emitter is connected to the ground and the collector is connected to the positive power supply VCC through a resistor which is called collector resistor RC. Also, I must tell you, don't try to simulate or fabricate this circuit because there are many lacuna in this circuit. This circuit I am showing you just to give you the concept of biasing. This is not actual biasing is not so simple. Anyway, transistor collector is connected to positive supply. So a positive current flows through this resistor RC, then through the collector base junction and then through the base emitter junction and then comes to the ground. And this current, say, is IC, right? And the potential drop across this resistor is RCIC. The remaining potential drops across the collector and emitter of the transistor, and this is normally given a name of VCE or collector emitter voltage drop. This is the base of the transistor, and to this base you put a bias VBB through a resistance RB. I told you in our last lesson why this resistance RB. This RB, if the RB is not there, then this base emitter junction is just like a diode, and this forward bias diode may conduct a huge current. So always there is a resistor RB here, theoretically. Practically, when we design, we shall see that RB need not be here. It can be somewhere else, but there should be a resistor in this path so that current is restricted. So this is the common emitter circuit where bias is VBB. Desired value is VBB. We shall see how we decide on VBB. This is a just a equation KVL, Kirchhoff's voltage loop equation through this line VCC to RC to collector to the transistor to the ground. It says VCC is equal to ICRC drop across RC plus VCE and then to, so this is a simple ohmic relation. This means if you just manipulate a little bit, IC is equal to IC becomes minus VC by RC or minus 1 upon RC VCE plus VCC by RC. Now look at this line. This is a y equal to mx plus c. It's a straight line equation. This is a straight line in the VCE IC axis. That means if you draw a graph with the x-axis VCE and y-axis IC, then this is a straight line, right? Like this. This is the x-axis VCE, y-axis IC, and this line is a straight line. You see, when IC is equal to 0, then RC gets cancelled and VCE becomes VCC. That means voltage across the transistor is equal to the supply voltage. That means this point is VCC. VCE is equal to VCC. And when VCE is equal to 0, then IC is equal to VCC by RC. That means this value when VCE is equal to 0. So this is a straight line, and since it is a Kirchhoff's law relation or ohmic relation, in this collector-emitter circuit, then you must agree that you may make any value of collector current IC, any value of VCE, any value of RC, whatever you do, at any point of time, the value of IC and VCE must lie on this red line. Shows that as IC increases, VCE decreases, and as VCE increases, IC decreases. This is the basic thing. The values of VCE and IC will always fall on this line. You cannot get out of this line. Get out of this. This is a straight ohmic relation. Next, we shall see. This line has a good name. It is called load line. It's a catchy name. And all through your analog electronics circuit syllabus, this load line, this term will come to you again and again and again. So please remember what is a load line. It is a straight line equation in the collector-emitter circuit, which gives a relation between any instantaneous value of VCE and IC. This is called a load line. Next, bias VBB create a current IB through the base emitter junction. Bias VBB will create a base emitter current IB, right? We have one ohmic relation, we are going to have another relation, right? This current IB flows through this base emitter junction. That IB, whatever bias you create, it creates the IB, and that IB will create a collector current IC according to the relation IC equal to beta IB. This is also a basic transistor equation. Of course, there is plus ICBU, all that. That is theoretical relation, but we can, for practical purposes, we can forget that reverse current between the collector base junction. right? So whenever you bias, there is a base current. That base current creates a automatic I value of IC. You cannot override that relation. IC is equal to beta I. So, and that value of IC also must lie on this red line. So you see, two relations are working together. Your bias VBB is creating a IB. That IB is creating a collector current beta IB. And that collector current must follow the Kirchhoff's relation of the collector emitter line. And that must follow on this. Now, the question that you will ask, if I give beta BVBB, the IC will fall on this red line where? In the upward side or downward side or middle side, where it will fall? It will fall on this line, but the question now is where? Where on this line? We shall find an answer to this question where. Because this is the transistor output characteristics, which you have already learned in your device subject. This output characteristics gives a relation of VCE versus IC for various base current IB. This is the maximum base current. This is less than that base current. And this is the minimum base current, etc., etc. So now you see, there are two things must join together somewhere. This IB that we have created by this bias VBB is one of these lines. Which line you have to find out? You have to calculate and find out this, your bias IB is this IB or this IB or which one? Which line? Of course, there are thousands of lines in between. Diagrammatically, only a few lines are shown. Which line? Let us say this is the line. This transistor characteristics you will get from data manual, or you can nowadays you can also get it from Google, the transistor output characteristics. Let us say this is the IB value that you have created due to bias VBB. And this value of IB is called IBQ. Q stands for the word quiescent. Quiescent. Quiescent base current. Let us say this is the quiescent base current, IBQ, which has been created. And since the point has to fall on the red line, let us say this is the point. This point is also called quiescent point. And since I think the quiescent spelling is difficult, so also we call it operating point. So you decide what is the operating point. This operating point, depending on the bias that you have created, if you create a higher IB, then operating point will be somewhere here. If you create a lower IB, operating point will be somewhere here. Now, for the sake of clarity of the drawing, I have shown you at the middle so that the drawing is not jumbled up, right? So this is the value of IBQ. And this IBQ creates a IC equal to beta IB. That IC must be equal to this value. This value of VCE or collector emitter voltage is called VCEQ. That means VCE quiescent. And that value of collector current is called ICQ or quiescent collector current. This IBQ or VCQ, ICQ decides, it is named at the quiescent point. Try to design a transistor-based circuit. Deciding the quiescent point or finding the quiescent point or operating point is your step number 1. And that point is called VCQ, ICQ. Right? Now, if we apply a signal voltage at the input. So what I am telling, you have given a bias VBB, which has created a current IBQ, and corresponding value of IC is this blue circle. The current is ICQ and corresponding VCQ is this. Now you apply a signal voltage like this I have applied here. You apply a signal voltage, is a varying voltage. You apply a signal voltage output. This it will create a varying base current. See, this base current IB is there, was created. This is the DC current which was created by VBB, and over and above IB, this varying signal voltage will create a varying alternating current here. And let's say this composite current is IBQ plus small ib. In normally, whenever we use small I, we means the alternating or varying part of the current, and small v is the varying part of the voltage. So now your base current is the DC current IBQ plus this varying component IB, which is a sinusoidal if your input is sinusoidal. So now you are no more on this line. You are now jumping from here to upward and to downward and to downward, upward like this. Because IBQ plus there is a varying IB voltage, base current. That means this operating point will now go on shifting from up and down and up and down and up and down like that as according to the signal voltage. Clear? I hope it is clear. The base current is IBQ plus the varying current IB. Automatically, according to this beta relation, there will be a ICQ plus a varying current IC. That means collector current will be DC component will be ICQ and the varying component will go on varying like this up and down. Right? Be the output here VO. Output here VO. In this particular circuit, since there is no other component, this VO is equal to VCE. So VO equal to VCE will be, go back to this relation, will be VCE will be VCC minus RCIC. VCC minus RC into collector current is now ICQ plus a varying component. Right? So it is VCC comes here minus RC ICQ minus RC small ic, that means varying component. And VCC minus RC ICQ, VCC minus RC ICQ is equal to VCQ. That means VCQ minus RC IC. What we find here? Look at this relation result here. Final output is a DC voltage, VCQ, minus a varying voltage. Minus a varying voltage. The varying voltage, its value is RCIC or pick of the IC. That means the output is varying voltage like this. The VCQ minus there is a variation. If you put an oscilloscope here, you will find a DC voltage, which is, and on the DC voltage, there is a variation like this. And we shall see later on. I think I have talked about it in my last lesson also. There, just simply put a capacitor, the DC will be blocked, and at the output, you get the AC out. So here, we find that means the output will have a varying component, RCIC, superimposed over VCQ, like this. This is the output. What your intuition says, if you want maximum possible variation, that means maximum output, then this blue point should be at the middle of the red line. Am I correct? I think you have already guessed. That is what I am going to tell you. That means in order to have a maximum possible varying component in the output, the quiescent point VCQ ICQ should be at the middle of the load line, should be at the middle of the load line. Because if your quiescent point is upward here, then you can vary only up to this point, because if you vary more than that, it gets saturated. Similarly, if your quiescent point is at the bottom somewhere here, your negative side, you can get only a small variation. So it should be at the middle. So what is the result we get here? We started our discussion. What is the desired value of the bias VBB? Answer to this question: the desired value of VBB bias is such that it supplies such a current IB to the base emitter junction that the beta IB, which produces the IC, is at the middle of the load line. So, detail of this we shall go while we learn the designing of the amplifier. We shall first find out what is the load line equation. Then we shall find out what is the middle point of it. Then we shall find out what is the value of IC. Then we shall find out what is the corresponding value of IB. Then again through circuit analysis backward, we shall find out what is the desired value of the bias voltage VBB. So I shall stop my lesson, this lesson here, with the conclusion that biasing is providing a suitable DC voltage, fixed DC voltage to the input or base of the transistor, so that the required value of collector current is produced, so that we get maximum output, maximum peak-to-peak output of the amplifier. So this lesson ends here. So in our next lesson, we shall see the various available schemes and techniques to create bias. Because as I said earlier also, that here I have used two power supplies, one power supply VBB, another power supply VCC. And no customer allows that, to give one power supply, two power supplies to one amplifier. Right? So there are techniques. Techniques means only circuit design techniques to provide the necessary base voltage, DC voltage at the base of the transistor, so that all conditions are satisfied. Okay? We shall finish it here, and in the next lesson onward, we shall see the various available biasing schemes.